So we'll begin, as we always do, in Massachusetts. And in particular, we'll start with the hero of our story, Bill Weld, governor of Massachusetts in the 90s. And there's Bill Weld right there. And let's talk about the Massachusetts Group Insurance Commission, the GIC. So in 1990, they decided to release anonymized data on state employees that showed every hospital visit. Now, I'm sure they wanted to justify, the bunch of you state employees getting rich off this group insurance. No. They wanted to show that this was pretty normal stuff. So they released the information, every hospital visit, but they anonymized it. They took out names and addresses and social security numbers. Okay, great. And, Bill Weld assured everyone that this was okay because, of course, it was okay. I'm sure he was told it was okay, and, he agreed this was okay. Anonymous data is anonymous data. No names in it. Someone went to a hospital on this date. Who knows who that was? Well, now we enter the evil villain of our story. Ooh, so evil. That's LaTanya Sweeney. At the time, she's a graduate student, and she requests the data. She's like, hey, this data's been released. Send me a copy of it. Now, she knows the governor lives in Cambridge, Massachusetts, a town of 54,000 residents and 7 zip codes. And so she pays $20 to get the complete voter rolls from the city of Cambridge. Okay, and this includes name, address, zip code, birth date, and sex. Well, let's see. She knows the zip code where the governor lives. She knows he's male. She knows when his birthday is. Only 6 people in Cambridge share the governor's birth date. 3 of them were men. Only 1 of the people in the medical data lived in his zip code. And so then she extracted all of the governor's medical records with diagnoses and prescriptions and sent them to the governor's office. She had de-anonymized one of the entries in those anonymized medical records. Somehow, our villain goes on to graduate in spite of making the governor mad, and Dr. Sweeney goes on to show that 87% of all us Americans can be uniquely identified with only 3 pieces of information: zip code, birth date, and sex. Uniquely identifies 87% of people in this country. Astonishing. Really fascinating result. Where are they now? Well, Dr. Sweeney is the Daniel Paul Professor of the Practice of Government and Technology at the Harvard Kennedy School in the Harvard Faculty of Arts and Sciences in the Department of Government. And Bill Weld was the last non-Donald Trump candidate to withdraw from the 2020 presidential election. Okay, so different career paths there. Maybe this was the result of that? Who knows? Anyway, I like to follow up with who these people are. Okay, and that takes us to talking about individual privacy and population data. So Bill Weld's information, his medical information, that's individual privacy. But the records of everybody who was a government employee, that was population data. How do those two play together? Suppose we build a data set of HIV positive individuals. We talked about this before when we talked about black box. People might reasonably be concerned about that information becoming public, right? How it would adversely affect them. Again, another argument for privacy, okay? And so over here is our slice of our little data set. Several rows. Each row has a series of features associated with it. Name, date of birth, state, blood type. Okay. Suppose we disallow queries on names, and we only return simple information computed from the data set. That sounds good. But suppose we ask the query, how many people in the data set were born between January 1st of 1991 and February 1st of 1991, reside in Massachusetts, and have blood type B? that row right here. This question is basically akin to asking, is this person in the data set? Has this person been diagnosed with HIV? If we get back the answer 1, we can be pretty confident. If we get back the answer 0, we can be pretty confident. Okay? There you go. So maybe we can use that even though the name is masked, even though it's been anonymized or our query doesn't let us get to the name, maybe we can use these other things as a proxy for the name. And that's what Dr. Sweeney figured out. Well, we can combat this, maybe, by never returning a result that is less than some number, right? If I do that query and there's only one person, I say too few results to return. And you may have seen some data sets that do that. Okay, fine. Maybe I can ask questions such that the combination of the answers reveals the presence or absence of the specific individual. I'm building the Venn diagram. Okay? And by doing that, maybe I can zoom in and pull the person of interest out. The point of all this is, what we want is the inability to determine if a specific individual is present in the data set. And this sort of problem can encourage people to decline to answer surveys, right? We're conducting a survey, and we ask you a question, and you think, who might see this data? Maybe I shouldn't answer. And so maybe you don't answer. That doesn't help researchers. How can we convince people that it's okay to answer our questions and to put their data in our data set and convince them that their data won't be exposed later? That's tough. And that takes us to part 2, statistical privacy. And a really clever invention. At least I think it's clever. So Stanley Warner was thinking about how to overcome non-cooperation in surveys. There are going to be people who, when you ask them the question, they're going to say, I don't want to be part of your survey because I'm scared of it. And okay, fine. Or they're going to say, they're going to lie to you on the survey because they're worried about their answer. There's always going to be trolls. We admit that. We accept that some people just want to watch the world burn. Fine. But for the rest of them, is there a way we can convince them that giving us an answer to a survey question can't come back and harm them? And maybe people decline to answer or fail to answer because they're concerned that their answer will be used against them. And that's a question of privacy, right? It's a question of privacy. Maybe if we can guarantee the privacy of the individual surveyed, we'll get better data. But we have to convince them. And that brings us to the spinner. So think about this for a minute. Suppose I want to know how common insider trading is. Insider trading is illegal. So I go out and I ask people, have you ever traded stocks using information not available to the general public? And they all answer, why, of course not. Never. No. Of course they're going to say that because insider trading is illegal. How do I get them to answer the question in a way that's useful? Okay, let's create a little spinner, right? So over here we have a notional spinner. We've got a little arrow we can spin, and we have some areas marked out, one labeled A and one labeled B. And we can control how much of this is A and how much of this is B. We might split it right down the middle, A and B. We might have a small sliver that's B and a big sliver that's A. We can control all of that. And so the point being, we can control the relative probability that the spinner lands on A versus landing on B, right? I spin that, and I either get outcome A or outcome B, and I can actually control the probabilities by controlling the relative amount of area for A and B. Ah, nice. But this seems off topic. What do we do with this spinner? Well, here's what we do. We divide our population into two groups. Group A, people who have committed insider trading. And Group B, people who have not committed insider trading. Okay. the questioner gives the participant the spinner, and then they leave the room, or they turn around, or they do something else, and the person they're asking the question of, they have the job of spinning the spinner and then answering yes if the spinner lands on their group. So let's say that you are an insider trader. You've done insider trading. You spin the spinner and it lands on B. So your answer is no. Let's say you spin it and it lands on A. Your answer is yes. But the person who's asking the question never gets to see the spinner. They don't know where it landed. All they have is a yes or no answer. And that doesn't reveal whether you committed insider trading or not. So you have plausible deniability. You sit there and you say yes. And yes could mean that you spun the spinner and it landed on A and you are an inside trader, or it could mean that you spun the spinner and it landed on B and you're not. And there's no way for the questioner to know the answer to that question without having seen what you did. Now, clearly, if P is 1/2, then you've got no information, right? The answer gives you no information. That's not useful. If P is 1, then the participant has no deniability, right? It's all A. And so you spin it, and the answer is A, and then you're like, either, yes, I'm an insider trader, or no, I'm not. And so we don't want that. We want something like what you see here, where there's a reasonable amount of plausible deniability. Because then, it's sort of hard to think about what you should say or shouldn't say. You're just going to spin the spinner and answer truthfully because that's easier. Okay. Did we learn anything from that? Well, clearly we agreed that the 1/2 case provides no information. The 0, or where everything is A, that provides perfect information. In between should provide some, but not all information. So let's think how to use that. 4 outcomes. Insider trader in A, yes. Insider trader in B, no. Not insider trader in A, no. Not insider trader in B, yes. And we know the probability P. So can we estimate the population statistic of being an insider trader based on this? Well, let's reason as follows. Let pi be the true probability of A in the population. That is, pi is the percentage of the population, the fraction of the population that is an insider trader. And let P be the probability of A on the spinner. We know that because we control that. Let x sub I be 1 if the ith sample is yes, if the ith person we asked said yes, and 0 if they said no. And we can compute probabilities like this. What's the probability that the ith person said yes? Well, it could be that they're an insider trader and the spinner landed on A and they said yes, or it could be that they're not an insider trader and the spinner landed on B. Either one of those would result in them saying yes. Same thing down here, the two options that result in saying no. So this is useful here. We know what these were. We know what P is. We don't know what pi is. So we have an unknown still living in this little set of probabilities. So there's a notion called the likelihood. Likelihood is the joint probability of observed data viewed as a function of parameters of your model. That may be a little hard to think about, but imagine in your head you've got a model, and the model has a parameter. I can turn that parameter. And as I turn the parameter, I get different kinds of outputs from my model. And what I want to do is I want to find the most likely value of the parameter that yielded the results that I'm seeing, right? The results I'm seeing are effectively the results of random sampling. So I can't just tell you what that value of the parameter is, but maybe I can tell you what the most likely value of the parameter is. How do I do that? Well, suppose we have a sample where there are n sample points, and of those, y report yes. What's the likelihood of observing that outcome? Well, it's like a Bernoulli trial. right? And so here's saying yes, say yes y times. Here's saying no, I say no n minus y times. And that's the full probability of seeing y yeses and n minus y no's. And I'm going to call that the likelihood. Now, in here I know p, I know y, and I know n. What I really want to do now is choose a pi such that L is maximized. And this gives us a maximum likelihood estimator, MLE, of pi. Maximum likelihood estimation is like the Fourier transform. It's almost magical in the way that it works. It's used everywhere. With a little calculus, we can get it, right? So going back, we can use logs to move these exponents down. We can do some other funky stuff here, and we wind up with this. The maximum likelihood estimator for pi is this ratio plus this ratio. And so we know p, we know y, we know n. We can compute this. Okay, and this gives us a value for pi, the maximum likelihood value for pi. Now notice that we have 2p minus 1, so if p, our probability for the spinner, happens to be 1/2, 2 times a half is 1, 1 minus 1 is 0, that's not going to work. So p can't be 1/2 because, again, there's no maximum likelihood value for pi there because we have no information. So there you go. Further, we can prove that the expected value of the maximum likelihood estimator in this case is pi. So it's an unbiased estimator for pi, right? Bias is deviation from the mean. Well, our expectation is the mean, so we're unbiased. Variance, a little different. Variance is the variance of the sample plus the variance of the spinner. And if the spinner has a fairly large area for B, it's close to 1/2, the variance is going to be high, and we're going to need a lot more samples to get our sample variance within bounds so that we can stop testing, or stop the sampling process and get a good estimate. So let's give an example to make this make more sense. Maybe suppose we sample 1,000 people, and one of those happens to be an insider trader. We don't necessarily know that. We're gonna play the role of the omnipotent observer, and we know that one of those people is. So we know what pi is. Pi is 0.001, right? 1 in 1,000. So let's let p, our probability for the spinner, be 0.75. Okay. So suppose everyone answers truthfully. Now, if you want to know what happens if people don't answer truthfully and how you incorporate that into your model, that's in the paper. He does consider the case. He says, some people just want to watch the world burn. He doesn't say that explicitly, but he does say, there's going to be trolls, and we have to account for that. And so he does. He estimates the amount by which this can preserve the answer. So in our case, about 750 times the spinner lands on A, and the respondent answers no. And about 250 times the spinner lands on B, and the respondents answer yes, right? Because most of them, nearly all of them, are not insider traders, except for our one inside trader who answers in the opposite. Let's suppose for him the spinner lands on A, and thus he answers yes. And so we end up with 251 yeses and 749 no's. We plug those values into the equation you saw previously, and our estimator of pi is 0.002. We're really close to the true value. And we only sampled 1,000 people, and we used we didn't do a huge amount of effort on this. The important thing is we have no way to discover, is there an insider, right? Our thing says there might be two. There might be two. Who are they? I have no way to know. I have no way to know. Would they be among the yes answers or the no answers? I don't know which one they'd be among. Right? And it turns out Thinking that there are two would be wrong, right? There's actually just one, and our variance would show that if we compute. I didn't compute it here for this. But wow, I mean, that's pretty darn close. And we preserved the anonymity of everyone who responded to the survey. So how many samples do we need? Well, that depends on the variance, which is higher and more samples are needed, the closer p is to half. Now, this all hints at a mathematical framework for privacy. And that's where we're going to be headed. Right? We're going to be thinking about ways in which we can guarantee privacy for individuals. And this is one clever way to do that from taking a survey. Let's think about maybe changing the process. Suppose we collect everyone's data and we just straight up collect it. We get the true answers for people. We collect it through whatever means. We collect your medical records, or we collect whatever. Right? We just get true data. But whenever someone generates a query, we spin the spinner. And if the spinner matches the answer, we respond yes. And if it does not, we respond no. This preserves plausible deniability for the information. And researchers can still use maximum likelihood estimation to get the true, or to estimate the true sample value. So we could turn it around, and what this is doing is it's sort of fuzzing the result before we hand it back. That's interesting. That gets at an idea that, maybe we can find a way to add deniability at different levels. So when we first used the spinner, right, we take a question and we added noise to that question, added some uncertainty to it before the data went in the database. Okay? So our database has deniability built into it. And if we do things correctly, we have to trust the data collection process. Right? I'm not secretly spying on you when you spin the spinner. We trust the data collection process to correctly add the right amount of noise. In that case, the data's got deniability built into it, and my work is done. This adds statistical noise to the entries in the database, and we can control how much we add. And that's neat. If we take a particular individual and add them or remove them, and there's plenty of people in there, the data should basically look the same whether or not the individual is included. Think back to the example we had for the insider trader. If I'd taken one of those data points out, would it have made a big difference? Probably not. And that data point could have been our insider trader. So, wow, that's a neat result. The other way, reversing the spinner, says I collect the data in reality. My database now has all this private information in it, but when I answer a question, I add noise to it, and the noisy result comes back that preserves privacy. Here I have to trust the database maintainer to properly and securely store the sensitive data, and I have to figure out how much noise to add later on. But we can probably figure that out. Okay, the result of a query should still not reveal whether or not an individual is in the set. Wow. Okay, all of this is sneaking up on an idea called differential privacy. And I think you can see how this is beginning to work, right? We're adding noise either at the collection or when we're querying the database. And that noise is going to act to preserve the privacy of the individuals. Suppose you have a database containing information that's sampled from some population. It's health data, or it's census data, or it's nationality data, whatever. A statistic is a quantity computed from a sample. So a statistic could be anything we can compute from the data in the database. We want to enable using the data while preserving the privacy of the individuals. So let's think about what privacy means in this context. Right? Some questions aren't privacy preserving, so we shouldn't be able to ask those questions and get a true answer. All right, we might ask, is Juan in the database? Is my boss Juan in the database? how many people in the database are 54 years of age, live in Pennsylvania, have the last name Salazar, and are positive for HIV. Okay, that will tell me whether or not a particular person is present in the database. And I shouldn't be allowed to select star from database where name equals something, right? That would be terrible. Those are all terrible questions to allow someone to ask. On the other hand, some statistics might be fine. Can I construct a set of queries such that if Juan is in the database, maybe I get a value S that's greater than a threshold N, and if he's not in the database, I get a value less than a threshold N? If so, I can answer one of the queries above and break privacy. This all seems like it's going to be really hard for me to figure this out or deal with this. Well, let's introduce some notions to make this more rigorous. Let's let D be a database containing Juan, and let's let D prime be a database equivalent to D, except that Juan is excluded. Let F be a statistic, and so F applied to D yields x1, and F applied to D prime yields x2. If x1 and x2 are sufficiently distinct, I can infer whether or not Juan is present in the database, and I can discriminate. But if we introduce random noise to the entries, and the difference in those x1 and x2 begins to go down, if I introduce enough random noise that I can't distinguish them, then it becomes hard. So that's the basic idea behind differential privacy. Next time we're going to talk more about it. So get ready for that.